kind of a worksheet over just looking at the units for all the different quantities, and then also maybe reminding ourselves of some of the related formulas, as well as certain things are vectors versus scalars. But we start with looking at displacement and position. Remember, displacement is a vector. It's a delta x. It's the difference between where you started and where you finished. It is still in meters. In a calculus way, you might say that the displacement is the accumulation of velocity over time. From a average velocity, the displacement over time, it's just what did you do and how long did it take you, and then that's on average your velocity. Position is really just kind of an x, and really it's in physics it's an x. In calculus in math we would use it more of a function, and we'd say x of t. And probably the classic standard position equation is just x naught plus v naught t plus 1/2 at squared. But you can also say x is equal to x naught plus what'd you do? And this v could be a function. So this is more of the constant acceleration idea, algebra, and then this is more of the calculus way of saying where you're located. Velocity, of course, is a vector. It's in meters per second. Again, if it's given any other way, change it to meters per second. This is our linear version. Velocity is how fast are you moving at the beginning, plus what did you do and for how long. And certainly the v-squared equation relates velocity to distance and acceleration rather than acceleration and time. Acceleration is also a vector. It's in meters per second squared, which is really, it's in meters per second. It's the rate at which you change your velocity. So if acceleration is, let's say, 4, that means 4 meters per second squared is 4 meters per second, which means you're increasing your velocity by 4 meters per second for every second. Again, acceleration by definition is the rate at which you change your velocity. The changing of a velocity is the accumulation of acceleration over time. So this is the calculus version. This is kind of the derivative version. The range of an object, we usually use capital R, which is also, of course, in meters. It's just how far something's horizontally gone on the ground. There's the range equation. Just remind yourself, we can only use that range equation if it's symmetrical. Angular displacement, well, angular displacement is just like displacement. Displacement is just linear displacement. We just don't say linear, it's just by default it's linear unless they say the word angular. So all of these guys are the exact same thing, just the rotational version. So angular displacement is the same as linear displacement. It just happens to be in radians, and it's the accumulation of angular velocity over time. The angular position, again, same position equation, except there's omegas and alphas instead of v's and a's. Angular velocity is in radians per second. It's how fast you're spinning. Again, same equations, just kind of the rotational version of those. All right, my next point here is these guys. Look, they're all in newtons. Well, of course they're in newtons. All of those things are just forces. They're just different versions of forces. An applied force is a push or a pull. The normal force is the force of a surface, and it happens to be perpendicular to the surface. That is what the word normal means. The force of friction, again, the force of friction is less than or equal to mu n. We almost always use force of friction is equal to mu n because that's the maximum the force of friction can be, but it really grows into that, right? It's the response to motion. And there is static and kinetic. Static is the stationary version. Kinetic is the sliding version. Tension, you use capital T, and it's just the force that a rope or a chain or a string causes on typically a box. The weight is capital M. The weight is just mg, unless you're doing big boy satellites, and then it's different. But for like roller coasters and such, the weight is just equal to mg. I always just put mg, but sometimes people put capital W. The drag force is typically negative bv, right? It's opposite and proportional to v. It is a vector, which is why the negative sign is there. But again, all of those things are just forces, so they're all in newtons. Centripetal acceleration, well, it's an acceleration, so it has to be in meters per second squared. And again, there's kind of two versions that are equivalent. You can do v squared over r or omega squared r. Acceleration, the centripetal acceleration for sure is inward. There's some force causing it to happen, which makes the thing move in a circle. The period, remember the period is just the time It's the time it takes to do one revolution. It's related to the frequency and the angular velocity. But again, it's just a time, so it has to be in seconds. Frequency is in revolutions per second. So if you look at revolutions per second versus radians per second, this formula makes sense because there are 2 pi radians in every revolution. So of course, omega is 2 pi f. They're both spin rates. One is in revolutions per second and one's in radians per second, and you're just basically converting revolutions to radians by that scale factor, which of course is 2 pi. Frequency is also the reciprocal of period. This is the time it takes to do one revolution, and this is the revolutions per second. So of course, these things are related. The next thing I'll point out is joules, 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 joules. Well, yeah, all those things are just energy or work. It doesn't matter what type of energy you have, it's in joules. So kinetic energy, elastic energy, gravitational potential energy, the work done. Remember, the work done is you doing work on something to give it energy. But again, the work you do is still in joules. You can do work by changing something's kinetic energy, lifting something. You can do work by stretching a spring or working against a force. It doesn't matter. There's all different types of work. Power. That's stupid. Excel filled that in for me. That's supposed to just be a capital P. You can fix that. I probably typed in capital P and Excel thought, oh, let's just fill in PE because that's what it was previously. Power, of course, is in watts. And again, think about what a watt is. A watt is a joule per second. It's how much work you're able to do per time period. This is the algebra version, kind of a work. If you wanted the calculus version, it would just be the derivative. And the flip side, the energy you use is accumulating power over time, using power over time. Now, algebra would just be power times time, but if the power is a function, then you have to use calculus. Momentum, this is making me upset. I'm not doing this video over again. That right there is supposed to be an S. I don't know why. I just typed in X. They're close, I guess, on the keyboard. But momentum, it's stupid. We don't give it its own unit. No one must have been famous enough for momentum. But momentum is a little p, and then it's kilogram meter per second. There's not a special unit. Just think of it. Momentum is clearly mv. M is in kilograms. V is in meters per second. So then momentum is in kilogram meter per second. And again, it's a vector. So we typically do x hat and a y hat. Impulse, well, impulse is the change in something's momentum. However, we don't usually use the same units of momentum. It does. We usually use Newton seconds. Because think about it, how do you change some momentum? You give it a force over a time period. There's the algebra version. There's the calculus version. So we typically refer to impulse as Newton seconds. And you could really use that same unit for momentum. Just it wouldn't make as much sense. So typically, momentum is referred to as kilogram meter per second. How many of those you got? And then impulse, the changing something's momentum, is applying a force for a time period. So how much you've done there is in Newton seconds. Torque, torque is in meter newtons, which is also really weird because remember it's a distance times a force. Torque equals R cross F, and we just gotta make sure they're perpendicular. Now torques cause I omegas, but what actually causes the torque itself is a perpendicular force with a lever arm. Rotational kinetic energy, look at that, energy, again, it's in joules. Of course it's in joules. It's energy, it just happens to be rotation. So it's a 1/2 I omega squared, and we're looking at like pulleys, discs, boards, balls, anything that is hoops, anything that's rotating is gonna have rotational kinetic energy now. The moment of inertia, again, think of the formulas. The formulas are all like 1/2 mr squared. So it's a mass times a distance squared. So the moment of inertia has units of kilogram meter squared. It's the rotational version of mass. Center mass, okay, that's in meters. It's a position, right? How you find it is you just do a weighted average. Again, but the units of center mass is just meters. Angular momentum, also dumb units. Sorry, but think about the formula. It's an R cross mv, so it's meters, kilograms, meters per second. Again, my bad, but no one was famous enough to get it named after. Satellite potential energy, you're like, oh, okay, that's fine. It's in joules. Of course it's in joules. It's energy, negative Gmm over R. Newton's law of gravitation, so the idea of a big boy force, well, it's a force, so it's still in newtons. So it's got it, in that case, it's Gmm over R squared, and we call that an inverse square law. If you're looking at the period for a simple harmonic oscillator, so it doesn't matter whether you're looking at a spring or you're looking at a simple pendulum, remember the period is the time, so it has to be in seconds. And then one of the ones I added at the end was the coefficient of friction. Remember, it is mu, and there's no units. It's the ratio of two forces. Just look at the formula. This is in newtons, that's in newtons, and this mu is just a coefficient. It's just a coefficient of the two materials, whether it's a block of wood sliding on wood or whether it's a plastic block sliding on glass. It's a function of the two different surfaces and how they interact with each other. Again, but mu does not have any units. So should be able to go through those. You can see a lot of those are just joules and newtons. And if they're not, then they better be the fundamental units of kilograms for mass, meters for a length, seconds for a time. And these can get tricky sometimes when they're giving you experiments and, I don't know, they give you the spring stretch so many centimeters. Don't use centimeters. You have to use meters. They might give you a smaller mass and they give it to you in grams. Don't use grams. It has to be in kilograms. You talk about a planet rotating. They might give you the period of the planet is like 4 days. You can't use 4 days. You have to change it to seconds. So in mechanics, I mean, everything is basically those three things: kilograms, meters, and seconds, and then other things are just variations of those. So a Newton, think about it, it's just a force. A force in itself is just an MA, so it's just a kilogram meter per second squared. That's what a Newton is. If you think of what a joule is a kinetic energy, so it's got to be a kilogram meter squared over second squared. So you can always break down the newtons and the joules and the watts in terms of what they really are. But again, those are famous enough and occur enough that we have special names for forces and energy, and power. But all the other stuff kind of just is a breakdown of the fundamentals. Okay, so be careful if they try to trick you with units. You have to know, and then I would apologize that I know I'm not as good as I should be when I'm on the board or even doing the keys during the year of making sure I always include units in my answers. But on the AP free response, you have to get into the habit of making sure your answers have units and they're the correct. And if it's a multiple choice question, every now and then they actually just ask you for the units of something. So did I have that in there? Oh yeah, I think I skipped that when we were doing this. This one, the spring constant. The spring constant, remember, just think F equals ma, and the force is negative kx. So it should make sense that k is newtons per meter. So that's a fun one that they could just ask you, what are the units for k, or what are the units for I? And you'd have to think those through. Always just go to the equation and break down the equation, and you should be good. But we have to make sure that as we practice for the AP test that we're using units on all of our answers on the free response.